Hello, and welcome back. In this and other future videos, I will be including some of my video dialogue notes. They are not exact copies taken directly from synthesis, but they follow very closely. Therefore, the theorem and equation numbers in the notes will most likely be different from those found in the book. We have now reviewed several different principles and concepts of QEC. We are now fully equipped to present an all-inclusive cohesive theory of QEC. We first begin by drawing a circle. We place a point at its center called the origin. The origin is always designated as being 0. In QEC, 0 is never null. There is only the 100% absence of something that is always replaced by 100% of its conjugate. Consider a conjugate as being an extreme. We next place the derivative of Euler's constant e to the 1 at the origin. Extending right, we then extend e from the origin to its outermost extreme, the intersection of the x-axis with the circumference. At the circumference, e forms its conjugate e star, where e star equals e to the 0 equals 1. Therefore, e star forms a radius of 1. Since e is self-conjugate, then at the circumference, e forms a double point. Starting from the left, we extend e from the center to the circumference. This forms the cosine. Starting from the right, we extend the conjugate of e star, from the circumference to the center origin. This forms the versine, where the versine is defined as the versine is equal to the sagitta equals 1 minus the cosine. A fully extended cosine and a fully extended versine spanning the space from center to circumference both form radii of 1. E may matriculate to any point within or upon the unit circle. We allow E to traverse along the circumference some radian arc length. At any such radian arc length, no matter its magnitude, is a quaternion. Therefore, any point along the circumference is a quaternion, as well as any 2 pi radian circle, as well as any object that may be measured in radians or degrees. Therefore, all platonic solids, conic sections, and any geometrical element constructed from these constructs may all be designated as quaternions. From some point along the circumference, we construct a normal extending from the point to the x-axis. This is the sine. From the origin, proceeding to the right, we draw a line perpendicular to the sine along the x-axis until this line intercepts the sine. This is the cosine. From the circumference, proceeding to the left, we draw a line perpendicular to the sine along the x-axis until this line intercepts the sine. This is the sagitta. The sagitta and the versine are identical, except the relationship of cosine to versine is horizontal, and the relationship of the sine to sagitta is orthogonal. The versine and sagitta occupy the exact same space. The sine and cosine form a right triangle. The hypotenuse of this right triangle is the tangent. The sine and sagitta form a right triangle. The hypotenuse of this right triangle is the secant. The secant forms a chord which defines the extremes of the quaternion arc length, which by definition is a quaternion. From the list of trigonometric identities, I is always perpendicular to the tangent. Several operations occur in the QECian unit circle acting synergistically and simultaneously. All processes begin at 0 degrees or 0 radians. They reverse at 180 degrees or pi radians. They then repeat at 360 degrees or 2 pi radian. Let's focus our attention on the unit radius, which is labeled as the black tangent. As the tangent revolves or precesses about the unit circle, its length always remains constant. Let's next focus on the red sine. Pay particular attention to its extreme ends. The sine grows from 0 at 0 degrees or 0 radians to a maximum length of 1 at 90 degrees or pi over 2 radians and returns to a value of 0 at 180 degrees or pi radians. The sine immediately reverses its direction of growth and once again reaches a maximum of 1 at 270 degrees or 3/2 pi radians, returning to a value of 0 at 360 degrees or 2 pi radians. The upper extreme of the sine accelerates and precesses along the circumference, while rectilinearly and simultaneously, the lower end of the sine accelerates along the x-axis. As the red sine accelerates across the x-axis, the versine increases in value while the cosine simultaneously decreases in value. When the sine reverses its direction of travel, going from left to right, then it is the versine that decreases in value as the cosine gains in value. Next, focus on the growth of the arc length or quaternion. As the tangent precesses about the circle, it grows to red quaternion. The same can be said of the sine. The red sign grows the red quaternion incrementally, forming the red circumference. Where the black tangent always remains constant, the green secant is constantly changing. At 0 degrees or 0 radians, it grows from 0 to a maximum length of 2 at 180 degrees or pi radians. It immediately reverses its direction of growth and once again reaches a minimum of 0 at 360 degrees or 2 pi radians. The red tangent, as I, is always perpendicular to the constant black tangent. In Quick, we will often designate the hypotenuse as being the tangent. However, the hypotenuse should technically be designated as the tangent line. Any and every point along the tangent line as hypotenuse is technically a tangent point. Therefore, a tangent line is a summation or concatenation of an infinite series of tangent points or tangents or tangent locations that sum or concatenate to form the tangent line as hypotenuse. The tangent is also defined as being a slope. A slope is the rate or fraction or quotient or ratio of a y value over an x value. Therefore, any and every point along the tangent line must be equivalent, since any and every point must have the same y over x value. Therefore, any and every tangent point that lies along or upon a given tangent line is equal. The arc length may be considered as a summation or concatenation of an infinite series of points or e's or e locations as e propagates along the circumference. Since the secant is a hypotenuse and every point along the hypotenuse must be equivalent, then the chord is a quaternion since every point along the arc length is a quaternion, since e is a quaternion. And since by the Pythagorean theorem the secant is the sum of the sagittal and the sine, then the sagittal and the sine must be quaternions. Given the trigonometric identities, then the rate of the sine of the sagittal forms a hypotenuse, which is the secant. Therefore, the secant is a quaternion. And just as with the tangent, every point along the secant is a quaternion. And since the unit sagittal and unit cosine span the exact same length, then the sagittal and cosine must be quaternions. And given the Pythagorean theorem, where the sum of the sine and the cosine equals the tangent, then the tangent must be a quaternion. And since all trigonometric functions may be defined in terms of the sine, cosine, and tangent, then all trigonometric functions and their identities are quaternions. And since E occupies a point on the circumference, then E and its conjugate are both quaternions, no matter their location. Therefore, any and every point within or upon the unit circle is self-conjugate E. Therefore, any and every point that lies within or upon the unit circle is a quaternion. Therefore, E, E star, I, pi, theta, 1, and 0 are all quaternions. Therefore, any and every point that lies within or upon the unit circle is a self-conjugate double point. Therefore, since any and every point within or upon the unit circle is equivalent to self-conjugate E, then any and every point within and upon the QECian unit circle must obey Euler's formula. Every quaternion is a derivative, and every derivative is a limit. A limit exists if and only if it obeys the following equation. Such a limit may be expressed as a difference quotient. The difference quotient is written as follows. Consolidating all our concepts, we derive the Versine form of the difference quotient. And its consolidated form is as follows. In constructing the animation of the limit, we utilize the slider, which turns out to be an excellent illustration of the operation of space and body centroids. These animations verify the validity of the centroid method of differentiation. We can now fully consolidate all our concepts into one comprehensive structure. Note how the black tangent is now subsumed within the tilde dash lines of the ICR. This indicates that the tangent and the ICR are Tavasian conjugates and polar opposites. One is the derivative and the other is the integral. Thus, at the ICR, the derivative and integral become indistinguishable. Also note how the red cosine dot and the red secant dot assume the status of plus or minus cosine in the following limit equation. Also note how they converge on the point limit 1, 0, satisfying the following limit equation. Plus or minus I always equals plus or minus 1/2 respectively. Thus, plus or minus I and plus or minus 1/2, in whatever form plus or minus 1/2 may obtain, is and will always be a Fermatian derivative. This then leads to the definitive statement of Quick. Therefore, formally, we may state the following. Quick is quintessentially trigonometric. The whole of trigonometry, and therefore the whole of Quaternionic or Eulerian differential calculus, is ensconced within Euler's formula. But Euler's formula may also be expressed as the ratio of two quaternions as follows. Therefore, quaternion is equal to alpha beta, which is equivalent to beta over alpha, which is equivalent to sine over the cosine, which equals the tangent, which equals f prime of x. Alternatively, it may be stated that Quick is a form of calculus that employs Euler's formula as the foundation of integration and differentiation. Therefore, we obtain the following mathematical distillation of Quick. This concludes our rigorous examination of Quick and QECian principles. In the previous video, we employed the law of exponents q to the n equals nq to solve the Biot conjecture. Let's explore this law in greater depth. There are 4 main rules of natural logs. They are as follows. Quick asserts that all unit quaternions are natural logs. Therefore, all unit quaternions will and must obey all the rules of natural logs or the law of indices. Here we present a proof of that assertion. As a corollary of that proof, we may state I is equal to the square root of -1, which equals -1 to the 1/2, which equals 1/2 times -1, which equals -1/2, which is equivalent to 2. In solving the Riemann hypothesis, it was shown that 2 applications of I operating on 1 yields -1. That's because I inherently precesses its operand, or the quaternion on which it is operating, 90 degrees or pi over 2 radians. So I would precess 1 to the I sign position, and then precess I to the -1 position. Thus, I times I equals I squared equals -1. Therefore, I equals -1/2. A much simpler and elegant method would have been to simply use the power rule of quaternions, therefore yielding I equals the square root of -1, which equals -1 to the 1/2, which equals 1/2 times -1, which equals -1/2. We are now fully equipped to prove the negation of Fermat's last theorem. But before we dive into the proof, first some background on Fermat's last theorem. Fermat's last theorem was another one of those famous long-standing conjectures that had eluded being proven for hundreds of years until in 1995, Andrew Wiles published a 100-plus page proof of Fermat's last theorem, proving Fermat was indeed correct, that no 3 positive integers, a, b, and c, can satisfy the equation a to the n plus b to the n equals c to the n for any positive integer value of n greater than 2. For this, he was rewarded the prestigious 2016 Abel Prize. It was only until I learned the power rule of quaternions that I realized that the answer to Fermat's conjecture had to be that the conjecture is false. Now, before I go any further, let me be perfectly clear. I am in no way saying Wild's mathematics is faulty. I am simply saying the mathematics he formulated does not definitively confirm Fermat's last theorem. And to prove that, in typical QECian fashion, we will begin by using very simple logic. Let's start with the most basic of proofs, a margin proof. You may ask, what is a margin proof? Fermat claimed, I have discovered a truly marvelous proof of this, which this margin is too narrow to contain. I consider a margin proof to simply be a short, concise proof. The margin proof that I will now present is based upon the Quaternion power rule, q to the n equals nq. Here we present the first proof. Again, I will leave it to you to study this proof at your leisure. This Fermat's last theorem margin proof can basically be summarized as follows. If the quaternions a, b, and c equal the integers 2, 3, and 5 respectively, each being raised to a power of 3, then using the Quaternion power rule yields the following. Q equals a cubed plus b cubed equals c cubed equals 2 cubed plus 3 cubed equals 5 cubed. But by the Quaternion power rule, then we have q equals 3 times 2 plus 3 times 3 equals 3 times 5 equals 6 plus 9 equals 15. Therefore, Fermat's last theorem is false. If you still aren't convinced about the power rule of the quaternions, then just make a, b, and c exponents and apply the power rule of exponents. This particular negation margin proof is a very elegant and concise way of establishing the negation of Fermat's last theorem. But I will introduce other proofs that are more detailed in order to further explore the properties of the quaternion and therefore the properties of the derivative. The Fermat key proof simply establishes that given the Pythagorean theorem, for any given c, there must be a corresponding sine and cosine. And if c is a quaternion, then the sine and cosine must be quaternions. Therefore, all three must obey the rules of quaternions. We now present the negation of Fermat's last theorem based upon Fermat's key. Having presented the Fermat key proof, we now present the negation of Fermat's last theorem based upon I to the 4. The I to the 4th power proof is simply an extension of the Fermat key proof. If I is a hypotenuse or tangent, as given by Euler's formula for quaternions, then it must have a cosine and sine counterpart. The number of each counterpart has to match the number of tangents. We now present the I to the 4 proof. So far, I've presented 3 separate negation proofs of Fermat's last theorem, all based upon the rules of quaternions. However, I'm sure there are still some of you who still remain skeptical, especially since these proofs challenge the established orthodoxy of contemporary mathematics. My presentation of these proofs is a very serious and grave matter. The stakes are astronomical. This challenge to the prevailing mathematical orthodoxy is not being issued frivolously or recklessly. I do so armed with a clear logical mind and rock-solid algebra. The proof of this negation must be ironclad and irrefutable, and so to that end, I will now present my definitive margin proof of the negation of Fermat's last theorem. Before we examine this proof, let's establish some background information and concepts. Conventionally, it has been taught that given a Pythagorean triple, if we square each of the 3 sides, we then generate 3 separate areas, each area being contiguous to its respective side. And if we add the area contiguous to the base with the area contiguous to the height, then the sum of those two areas equal the area contiguous to the hypotenuse. Quick interprets the Pythagorean theorem differently. In fact, we shall refer to our interpretation of the Pythagorean theorem as the diagonal rule to distinguish the quick interpretation from the conventional interpretation of the Pythagorean theorem. The diagonal rule is a forerunner of the Pythagorean theorem, used centuries before the birth of Pythagoras by ancient Chumedians and Babylonians. The Chumedians are the people of Kemet, which included the ancient nations of Nubia, Cush, and Egypt. Here's how the two rules differ. The Pythagorean theorem uses linear measures to measure the magnitude of its components almost exclusively. Now, what do I mean by linear measure? Generally, I mean length, like using a tape measure to measure how long something is. But it can also mean how many individual units are counted. The diagonal rule uses both length and area to measure its components. This dual measurement is called quadrants. Quadrants can be either length or area. To illustrate these differences, let's start with a simple Pythagorean triple right triangle 3, 4, 5. Both the diagonal rule and the Pythagorean theorem says that 3 plus 4 equals 5. The Pythagorean theorem says if we add side 3 as a linear measure to side 4 as a linear measure, both sides being at a right angle to one another, then we obtain a hypotenuse of 5 as a linear measure. Thus 3 feet plus 4 feet yields a hypotenuse of 5 feet. The quick diagonal rule sees 3, 4, and 5 as initially being square measures. These square measures are called quadrances. The quick diagonal rule says if we add the area or a quadrant of 3 to the area or quadrants of 4, we obtain the area or a quadrant of 5 that happens to be contiguous to the hypotenuse of 5 feet. Thus 3 square feet plus 4 square feet equal 5 square feet. It is at this juncture that the two rules distinguish themselves one from the other. The Pythagorean theorem says if we square the length of 3 feet and form an area represented by 9, and if we square the length of 4 feet and form an area represented by 16, we may add these two representations and form an area represented by 25, such that one of its sides is formed by the hypotenuse. Now, I was very specific in my use of language. The measure of 9, 16, and 25 are not square areas. The linear measure of 9 represents 9 individual 1 by 1 square foot tiles that will cover 3 square feet. Therefore, we may regard 9, 16, and 25 as scalars or tensors that count unit 1 by 1 foot tiles. Thus, as previously asserted, the Pythagorean theorem uses linear measures exclusively. This is a distinction that is very seldom taught in our math classes when studying the Pythagorean theorem. The quick diagonal rule says that if we square the linear measures of 3 and 4 respectively, we form quadrances consisting of a linear measure 3 squared equals 9 and 4 squared equals 16 respectively. Thus 3 may represent a quadrant of area 3 square feet or a quadrant measuring a length of 9 linear feet. Where the Pythagorean theorem uses linear measures exclusively, the diagonal rule uses quadrances exclusively, which may be either linear or square measures. Adding these two linear measures of 3 squared equals 9 feet and 4 squared equals 16 feet forms a hypotenuse of a similar Pythagorean triple. Such a hypotenuse will have a linear measure of 25 feet. It is this aspect of the diagonal rule that makes it uniquely distinct from the Pythagorean theorem. Thus, we may express this aspect of the quick version of the diagonal rule as the diagonal rule of secants. Formally, we may state the diagonal rule of secants as follows. The square of the hypotenuse of a Pythagorean triple as a linear measure is called a quadrant. Such a quadrant will form the hypotenuse of a larger, similar Pythagorean triple. Let's now go through the proof step by step. Let's start with a simple Pythagorean triple right triangle 8, 15, 17. And by the Pythagorean theorem, we square all the sides. And in squaring all the sides, each side generates its own separate area. Now, even though the Pythagorean theorem allows us to form these areas, who says that squaring the sides has to be an area? Why can't it be a linear measure? What is preventing us from regarding 17 squared as 289 linear feet as opposed to 17 square feet? Quick says there is nothing that mathematically stops us from taking this approach. In fact, this is generally how we regard squaring the sides when given a squared plus b squared equals c squared. For example, given a 3, 4, 5 Pythagorean triple, then by the Pythagorean theorem, we compute 9 plus 16 equals 25, a linear measure. This is a summation totaling 25 individual 1 by 1 unit tiles. In Quick, we continue this practice by using the diagonal rule and quadrants. We say quadrants is the actual linear measure of a side squared. That is, 8 feet times 8 feet equals 64 linear feet. And so in Quick, the quadrants could be 8 or 64. In Quick, quadrants is just another way of stating I equals jk, or line I equals area jk, or E equals E star. This must be the case since the hypotenuse of any and every Pythagorean triple must find expression in both the QECian unit circle and Euler's formula. Therefore, the linear quadrants of 17 squared equals 289 forms the hypotenuse of a similar right triangle 161, 240, 289, which is also a Pythagorean triple. And if we square the sides of this 161, 240, 289 Pythagorean triple, we then obtain Pythagorean triple 161 squared, 240 squared, 17 to the fourth. And so we have taken the hypotenuse of Pythagorean triple 8, 15, 17 to the fourth power and created another Pythagorean triple whose sides have been squared. However, we encounter a major discrepancy. Even though 17 to the fourth power is indeed 289 squared, we see that 8 to the fourth power does not equal 161 squared, and that 15 to the fourth power does not equal 240 squared. This discrepancy would seem to indicate that Fermat's last theorem is indeed true. But this can be remedied by introducing the difference of two squares. The difference of the squares is given as a squared minus b squared equals a plus b times a minus b. And given the difference of the squares, we see that 161 can be factored into a difference of the squares quantity. 161 equals 15 squared minus 8 squared. We also see that 161 equals 15 squared minus 8 squared is the conjugate of 17 squared equals 15 squared plus 8 squared. And it is this insight that provides us with the key to solving the conjecture. Squaring 161 equals 15 squared minus 8 squared reintroduces the conjugate of the conjugate. 8 squared plus 15 squared equals 17 squared, all squared. And so now we can generate the solution. Using the quadrants of the Pythagorean triple 8, 15, 17 as a linear measure, we generate the hypotenuse of Pythagorean triple 161, 240, 17 squared. Expressing the quadrants of 161 as a difference of the squares, we square it and add it to the square of the quadrants 240. This sum is a linear measure, but yields the same result as the area 15 to the fourth plus 8 to the fourth equals 17 to the fourth equals 289 squared. And so, from the following equation we see, if A equals 15, B equals 8, C equals 17, and N equals 4, then Fermat's last theorem is false and thus negated. And there you have it, an exquisitely simple 9-step margin proof that could actually fit within the margin of a book, concise and precise. This negation of Fermat's last theorem actually establishes and proves Johnson's theorem and the diagonal rule of secants. Johnson's theorem states that some three positive integers, a, b, and c, may satisfy the equation a to the n plus b to the n equals c to the n for any positive integer value of n greater than 2 if integers a, b, and c obey Euclid's formula. Let's try to prove Johnson's theorem by further exploring the concept of quadrances. Both the Pythagorean theorem and the diagonal rule of secants support this illustration of a Pythagorean triple. The Pythagorean theorem emphasizes that a linear measure of 8 feet added at a right angle to a linear measure of 15 feet results in the formation of a hypotenuse having a length of 17 linear feet. The diagonal rule of secants emphasizes that contiguous to each of the linear measured sides of an 8, 15, 17 Pythagorean triple, there exists an area or quadrants measuring 8, 15, and 17 square feet respectively. The Pythagorean theorem emphasizes that each side of a 8, 15, 17 Pythagorean triple may be squared, and the squaring of these linear measures results in the creation of 3 other respective linear measures. Each squared linear measure is a summation of a collection of 1 by 1 individual square units. Thus, 8 squared is 64 individual 1 by 1 units that will cover an area of 8 square feet. The diagonal rule of secants emphasizes that each side of a 8, 15, 17 Pythagorean triple may be squared, producing 3 squared linear measures. The square of the base and height as linear measures sum to produce the linear measure of a hypotenuse of a similar Pythagorean triple. Thus, 8 squared plus 15 squared equals 64 plus 225, which equals 289, which equals 17 squared linear feet. Given an arbitrary pair of integers m and n, with m greater than n, which is greater than 0, and where a, b, and c are also integers, then Euclid's formula states that the integers a equals the quantity m squared minus n squared, b equals the quantity 2mn, c equals the quantity m squared plus n squared, all will form a Pythagorean triple. The diagonal rule of secants is the linear summation of quadrances. This summation is a direct result of Euclid's formula, which is ultimately a result of Euler's formula, which is ultimately an expression of the Quaternion equation I equals jk. And from this we may generate and consolidate the Pythagorean theorem or diagonal rule along with the diagonal rule of secants. One may argue that the diagonal rule of secants is simply an alternative expression or corollary to Euclid's formula. However, I have elected to separate the two for a very specific reason. Euclid's formula provides for an orderly generation of Pythagorean triples in general. But the diagonal rule of secants is very specific. It algebraically constructs an infinite succession of similar Pythagorean triples. It generates a nesting succession of similar Pythagorean triples based upon the concept of quadrances. What becomes clear is that in both Johnson's theorem and the diagonal rule of secants, the foundation of these two processes is Euclid's formula. Euclid's formula, expressed in terms of the Pythagorean theorem, is given as follows. However, Euclid's formula must also be expressible in terms of the diagonal rule of secants or quadrants, and the consequence of that requirement is that a squared and b squared must be added as a linear sum to produce a hypotenuse of a similar Pythagorean triple whose linear measure is c squared equals uppercase C, where uppercase C is the length or quadrants of the larger generated Pythagorean triple. For instance, consider the following consolidation. The last equation of this consolidation perfectly satisfies the form of Euclid's formula. That is, we shall allow 15 and 8 to equal m and n respectively. Therefore, given the following, we then obtain the following. In this form, we generate the sum of two linear measures that sum to the length of the hypotenuse of a Pythagorean triple. Thus, given a squared plus b squared equals c squared, then 161 squared plus 240 squared equals 17 squared equals the linear measure of a Pythagorean triple hypotenuse. Euclid's formula will always generate a Pythagorean triple, however m and n are arbitrary and must first be deduced. The modified form of Euclid's formula, or the diagonal rule of secants, will allow us to generate an infinite number of Pythagorean triples as long as we have two sides of an initial Pythagorean triple. From this initial triangle, we may generate an infinite nesting set of similar Pythagorean triples. Thus may we state Johnson's theorem. Some three positive integers, a, b, and c, may satisfy the equation a to the n plus b to the n equals c to the n for any positive integer value of n greater than 2 if integers a, b, and c obey Euclid's formula. Before we proceed any further, we must first address the contemporary convention of naming any right triangle having three integer sides a Pythagorean triple. It's obvious, and will be shown to be the case, that Euclid's formula is a much more fundamental treatment of such triangles. It will also be shown that Euclid's formula actually predates Euclid. To continue to call a squared plus b squared equals c squared the Pythagorean theorem, and triangles such as the 3, 4, 5 triangle a Pythagorean triple is just wrong, particularly when Pythagoras had absolutely nothing to do with their being discovered. It ignores and diminishes the work of the original discoverers. Also, the diagonal rule predates both Pythagoras and Euclid by thousands of years. I will be examining Euclid's formula in great detail. The result of this examination will be the discovery of novel methods of applying Euclid's formula. In Quick, we stress above all else, obey the rules, be logical, and use common sense. To continue to apply the misnomer of Pythagorean to these impending developments is not logical, and so to that end I will make a few suggestions of alternative adjectives to describe these triple triangles. One of my favorites is an M&N triple. Or we could, of course, just simply drop the name of any putative discoverer and just call them triples. Or we could use a name such as diagonal or Comedian or Egyptian or Mesopotamian or Chinese triples or even Eulerian or Euclidean or Johnsonian triples. At least when applying these personal names, we are recognizing that the math associated with these triples are the result of some mathematician's work who was actually instrumental or even tangential in the math's development. Now, having said all that, I am not naive enough to think that mathematicians, scientists, and students will suddenly stop calling Pythagorean triples Pythagorean triples. Tradition, habit, and convention is just too strong. The name Pythagorean theorem is locked and rooted into our mathematical vocabulary, but at least I have provided you with a logical rationale for having it replaced and a few viable alternatives. Let's go back to Johnson's theorem. Some three positive integers, a, b, and c, may satisfy the equation a to the n plus b to the n equals c to the n for any positive integer value of n greater than 2 if integers a, b, and c obey Euclid's formula. And from Johnson's theorem, we may derive 15 to the fourth plus 8 to the fourth equals 17 to the fourth. Now, while establishing the negation proof of Fermat's last theorem, if you didn't wonder about this equation when I first derived it, without benefit of Euclid's formula, then you have to be saying to yourself by now, what in the hell is this thing? And yet, the algebra is ironclad and irrefutable. And so we are left to ponder the quote of Arthur Conan Doyle. When you have eliminated all which is impossible, then whatever remains, however improbable, must be the truth. It is at this juncture that we began to get a taste of the powerful fungibility of quaternions. All quaternions are linked by E and the unit circle. One quaternion begets any other quaternion. Any trig identity may yield some two other trig identities. Quaternions do not discriminate. What's good for the goose is good for the gander. If a trig identity is equivalent to another trig identity, then Euler's formula means it. If I equals jk, then Euler's formula means it. If either point equals E the area, then Euler's formula means it. No exceptions, no excuses. A consequence of this powerful display of fungibility, that is, quaternions morphing into and out of each other continually, is that mathematicians and students can very easily get lost and confused while trying to navigate their disorienting pathways. That is why, in these introductory stages, we will stick strictly with the most basic of Quaternion algebra. And so we are forced to conclude that this fourth power thing actually exists. But what is this fourth power thing? This is where we now introduce Baker's definition of a quaternion. A quaternion is a scalar or vector or a combination of the two. After doing a considerable number of quaternion calculations, it became obvious to me that the practical distinction between scalar and vector was almost non-existent. What I mean is, whatever a vector can do, a scalar can and must do. Now, the final outcome of these processes might not look the same or be performed in the same manner, but both scalar and vector are quaternions, and therefore both are required to behave in the same manner. And so the sign accelerating across the x-axis as the versine is the same as the sign precessing along the circumference as the sign. The horizontal versine is a scalar, and the vertical sign is a vector. These are two completely opposed methods of acceleration, yet both accomplish the same function, the acceleration of the sign to a specific location in exactly the same amount of time. And even though intuitively I knew that a scalar had to act like a vector, even though they were conjugates, I couldn't really prove it mathematically. This is called a conjecture. Norman Wildberger has an extraordinary video lecture series detailing the discovery and use of his inspiring mathematics called rational trigonometry. His use of quadrances, terns, and spreads actually expresses the algebra of quaternions. Now, to be clear, he never explicitly says that this is what his rational trigonometry does, but for me, it was his rational trigonometry that actually proved the equivalency and fungibility of vectors and scalars. Besides, calculus is trig, so whatever concepts Wildberger has developed in his rational trigonometry, they must find some expression within QECian. Just like with quaternions, you will find quite a few definitions of vector, versor, scalar, and tensor. I have no doubt that these definitions are correct. However, I have little faith that most students can intuitively grasp what the definitions are actually trying to say. Generally, the scalar lies along the x-axis and the vector lies along the y-axis. However, there are no preferred axes in QECian. All axes are equivalent. The y-axis is no more preferred than the x-axis. A scalar is no more preferred than a vector or versor. We are conventionally taught that a vector is some quantity or entity or line that points in a certain direction. In QECian, a vector is a quaternion that matriculates from point A to point B, its line of travel pointing in a specific direction. In QECian, a quaternion is direction. A versor is a UQ or unit quaternion or operator. It precesses a scalar, which is the operand. A tensor is a pure number that indicates how large or how small something is. It ostensibly has no operational power. However, whatever an entity may be it tensor, scalar, versor, vector, big or small, left or right, up or down, rational or irrational, transcendental or integer. Once it enters the unit circle or the plus or minus 1 unit spheres, it then becomes a quaternion, and as such will behave as a quaternion, and therefore will and must obey all the rules of quaternions. And so, given the background information in Baker's definition of a quaternion, we may parse an earlier derived equation as follows. But earlier we established the following. And given Euclid's formula, where a equals m squared minus n squared, b equals 2mn, and c equals m squared plus n squared, we then obtain the following. Therefore, we may augment this following equation to read as this equation. We therefore generate three types of diagonal triples. And so we say again, a quaternion is a scalar or a vector or a combination of the two. Triples A and B actually exist. They may not manifest as conventional triples, but algebraically and trigonometrically, they do and must exist. Now, one of the immediate consequences of this examination is that Euclid's formula suddenly takes on a whole new meaning. It is much more expansive and fundamental than how it's been characterized in contemporary mathematics. Standard M and N tables are constructed by arbitrarily finding what values and pairings of some M and N will generate diagonal triples. This is a perfectly valid way of generating triples, but a much more simple method is to simply make M and N the actual sides of a triple. In so doing, we may then generate a nesting succession of similar diagonal triples. And as important as this discovery might be, our major discovery is that A, B, and C are not just sides. They are actually diagonal triples. And so we have established that side A is equal to 15 to the fourth plus 8 to the fourth equals 17 to the fourth, which is a scalar. We have also established that side B is a vector and is defined by the following equation. It's quite easy to see how this vector manifests itself. It is simply the plus or minus cosine and the plus or minus secant, conversion on the points plus or minus 1 as they matriculate across the x-axis. Therefore, minus the quantity 2 times 8 times 15 squared is C approaching from the right, and the quantity 2 times 8 times 15 squared is C approaching from the left. Thus we obtain the QECian continuity equation given as follows. Now, even though those oscillating C's look nothing like a triangle, at the end of the day, that interaction of C's is still representative of a zero limit, which is representative of a derivative, which is representative of a tangent, which is representative of a hypotenuse of a diagonal triple, which again is verified by Euclid's formula, which finally leads us to side A. What exactly is 15 to the fourth plus 8 to the fourth equals 17 to the fourth, which equals side A? Quick finds that the diagonal triple 15 to the fourth plus 8 to the fourth equals 17 to the fourth equals I to the fourth, which is A at 2 pi radians. This in turn is simply the diagonal triple 15 plus 8 equals 17, which equals I, which is A at 0 pi radians, after having matriculated twice across the diameter of the unit circle. Just as the cosine and secant matriculates twice across the diameter to converge upon plus or minus 1, then side A, or a diagonal triple, must also duplicate this process. To better understand this concept, let's revisit the I to the fourth power proof. Recall that it is given I squared equals -1, therefore I to the fourth equals 1. Therefore, as a unit quaternion, I to the fourth equals 1 must find expression as a hypotenuse in the unit circle. Since I equals jk, then I to the fourth equals jk to the fourth equals j to the fourth times k to the fourth, which is equivalent to j to the fourth plus k to the fourth. Therefore, in the unit circle, it must be the case that e to the I theta equals I to the fourth equals j to the fourth plus k to the fourth, which is equivalent to the cosine theta to the fourth plus var epsilon sine theta to the fourth equals 1. If we allow the secant as coord to represent the hypotenuse of a diagonal triple, then we see that its hypotenuse extends the entire diameter of the unit circle, reaching a maximum at -1, 0, which coincides with the following equation. Both quaternions then reverse direction and return to their starting point 1, 0. The diagonal triple starts as 8 plus 15 equals 17. It traverses the full length of the diameter where it reaches a maximum of 8 squared plus 15 squared equals 17 squared. It then begins its return trip and reaches a maximum of 8 to the fourth plus 15 to the fourth equals 17 to the fourth at its starting point having completed a round trip of 2 pi radians or 360 degrees. But this return triple is the same as the initial triple, a plus 15 equals 17. And so now we may express the QECian continuity equation in terms of Euclid's formula as follows. We may also express it in terms of the oscillating triangles. Now up to this point, I have deliberately avoided rules number 3 and 4. Quaternions do not commute. Ij does not equal ji. Ij equals minus ji. Even though it was never mentioned in the previous videos, this is the true basis for replacing the conventional form of the continuity equation with the quick version. The cosine going to the left does not and cannot behave like the cosine going to the right. They do not commute. And the reality of this non-commutativity fact is expressed in the following equation. Here we seemingly face a dilemma. Conventional quaternion algebra has it that as long as we remain in the plane, we may ignore the non-commutativity rules of quaternions, that the mathematical actors we will be dealing with will be complex numbers and not quaternions, because we are restricting ourselves to operating within the complex plane. Complex numbers commute. Therefore, the conventional rationale is that there will be no unit quaternion UQ. There will be no quaternion I, but rather the complex number the square root of -1. Again, I repeat, once an entity enters the unit circle or plus or minus 1 unit spheres, it will and must obey all the rules of quaternions. Complex numbers are a subset of quaternions. So are integers. Both may express their subset of rules freely within the unit circle. However, they are still bound by the rules of quaternions. This will be proven in a later video. Ostensibly, the unit circle is two-dimensional and therefore supports the complex numbers and therefore bypasses the expression of the UQ or unit quaternion. However, quaternions are four-dimensional, and the existence of a conventional two-dimensional plane is actually equivalent to a three-dimensional quaternion sphere. To illustrate, consider a typical three-dimensional XYZ coordinate system. We attach the center of a circle to the z-axis. We allow the z-axis to act as an axle or UQ or versa. And turning the axle, the circle now rotates in a two-dimensional plane, the XY plane. That is, we rotate the circle about the z-axis. We now take that same spinning circle and using the y-axis as the UQ, we rotate the spinning circle about the y-axis. The circle now precesses in both the XY plane and the XZ plane, occupying all three dimensions, X, Y, and Z. But we are still allowed to notate this collection of XY and XZ spins about the x-axis. This creates a fourth dimension along the YZ plane. Thus, quaternions occupy a four-dimensional space and are therefore four-dimensional. The four-dimensionality of quaternions is represented by the plus or minus 1 unit spheres. A four-dimensional unit sphere consists of a sphere occupying the three dimensions of volume, which is equivalent to XYZ, which is equivalent to IJK, which equals -1, plus a point center origin that occupies the fourth dimension. The rules of quaternions do not restrict the expression of other algebras. They are not mutually exclusive. The rules of quaternions are not fleeting. They are not episodic or intermittent or arbitrary. If quaternions exist, then they will and must exert. And no better example of this is the existence of the QECian continuity equation and the negation of Fermat's last theorem.